To understand the modern obsession with Tesla, start with one specific idea: buying a car that earns money while you sleep. Elon Musk's vision repositioned the company as an artificial intelligence developer, using vehicles as the primary hardware for a global neural network. In this model, owners would send their cars out as autonomous robotaxis, generating income as they transport passengers. Early software updates fueled widespread public optimism. Millions watched videos of these vehicles staying in lanes, recognizing stoplights, and navigating complex highways with apparent ease. Every successful update created a powerful assumption: truly driverless cars were essentially a finished product, nearing a final, inevitable release. But a significant caveat remained hidden behind the system known as full self-driving. The software still hinges on an alert, responsive human driver sitting behind the wheel, ready to take control. There is a vast structural gap between a system built to support a driver and a system built to replace one. One keeps a human in the loop to correct mistakes. The other operates entirely on its own. Crossing that final gap between human assistance and total replacement has proven to be a punishing engineering challenge. Autonomous systems must navigate the infinite chaos of the real world, a landscape of unpredictable situations that engineers call edge cases. Heavy rain can distort lenses and severely limit a vehicle's field of vision. A blanket of snow erases critical infrastructure data, hiding lane markings while simultaneously compromising the physical traction of the tires. Temporary road closures, heavy machinery, and shifting construction barriers force the software to navigate around obstacles it has never seen before. And in dense urban environments, the software must instantly anticipate the unpredictable movements of thousands of pedestrians and cyclists. A fraction of a second's error in any of these scenarios carries severe consequences. Because of that reality, regulators worldwide demand near-perfect safety standards before a driverless car is ever allowed on public roads. To solve this, most of the autonomous driving industry has spent billions of dollars mapping the world with external hardware sensors, specifically LiDAR. Tesla took a different path, relying almost exclusively on cameras feeding a central neural network. Humans navigate using only their eyes and brain. Therefore, an AI trained on billions of miles of real-world driving video should eventually learn to do exactly the same thing. Critics argue that relying completely on cameras makes navigating extreme edge cases, like sudden sun glare or heavy snowfall, highly difficult without secondary hardware to back it up. This intense technical debate leaves investors caught in a cycle of extreme optimism followed by missed deployment deadlines and renewed software improvements. The industry shift suggests that software superiority, rather than mechanical engineering, has become the primary metric for automotive success. The trillion-dollar incentive driving this gamble is immense. Achieving true autonomy at scale means consumers could stop buying family vehicles, shifting to an on-demand network of driverless cars moving in perfect synchronization. This leaves Wall Street and consumers asking the same question: is Tesla still a car company? The outcome is binary. If their AI succeeds, the company's valuation operates on an entirely different scale. If it fails, they will eventually be judged by the harsh, traditional metrics of terrestrial manufacturing. The final verdict won't be decided by stage presentations or promotional videos. It will be decided by the cold proof of safe, reliable operation on actual city streets. This specific pattern, committing to an extreme engineering goal and iterating through public failures, is the defining characteristic of Elon Musk's ventures. We see the same high-stakes architecture at SpaceX. SpaceX has already established a foundation of reliable operations in orbital transport, successfully launching and landing its rockets time after time. But the next leap is significantly larger. The Starship program is designed for deep space travel and eventual Mars colonization. Is Musk's space company delivering on these promises faster than Tesla? Or is it trapped in the exact same cycle of delays and engineering hurdles? The relentless collision between this extraordinary ambition and the harsh engineering reality is exactly where our investigation goes next.